Okay, so let's proceed. So after network planning, the next phase is network design. Network design. I hope you still remember PDI or I. So we say that we normally do PDI or I. So we begin with planning, then design, then implementation, uh, then operation and maintenance. Then what was the I? Improvement, something like that. So right now we are on design, network design. This is quite a long topic, so we're going to do it in several bits because it's quite wide. Actually, it has about 121 slides and has a lot of details. So in the forward, so in the design phase, we perform network designs based on the project requirements and guidelines that were specified in the planning phase. In the design phase, we determine the device selection. So this is where we go deep into technological specifications. So we select the device, we come up with a clear technological roadmap, we refine the network functions and performance specifications. So by the end of this chapter, you should be able to do all this, quite a long list. If you're there, you can help us, a volunteer.
Objectives.
Mm-hmm.
Upon completion of this section, you'll be able to understand common network types,
Yes.
understand each layer of the network design,
Uh-huh.
understand the common products and technologies,
Yes.
be familiar with advantages and disadvantages of common protocols,
Yes.
be familiar with comprehensive application of each technological module,
Mm-hmm.
master the network design and methodology.
Yeah, the network design methodology. Thank you very much, Owen. Okay, now let's begin with an overview of network design. Now, in the network phase, in the network design phase, customer requirements are obtained in the network planning phase. That were obtained actually in the network planning phase are implemented through technological methods. So the requirements are now implemented. So that is what we do during the design phase. Now, network design generally follows the modular design principle. The modular design principle. That means that you're able to divide the project into different modules, as we discussed in the previous chapter. So after design, network modules are then integrated. So remember, for example, we talked of the wireless module, the LAN module, the WAN module, the security module, so something like that. So they're implemented in a modular design principle. Now, network design deliverables must be standard, detailed, clear, and can be implemented. So in order to achieve this, the recommendation is that the network designer needs to have the following characteristics. Number one, they need to be familiar with network products. So the network designer must be familiar with network products. Other than being familiar with the network products, and still related to network products, they must be able now to select the proper products during the solution design for this project. So this must be a professional, a network engineer, trained network engineer, like you guys now. Now, number two, they must understand the available network technologies. and use the proper network technologies for this particular scenario. They must also have certain project experience. So this is what some of you might not have. Yes, you have the knowledge, you're familiar with network products, you have understood network technologies, but you don't have experience. So again, it might be difficult for you to implement a new network project from scratch. So as a network company entrepreneur, when you're involving techies to implement a network engineering project, then you must ensure that they meet these characteristics. They are familiar with the products, understand the network technologies, and they have some experience with implementing network engineering projects. Okay. Now, generally, the network design is divided into three main modules. Now, the first module is what we are going to deep dive in, is what we call the physical network design. The second one is what we call the logical network design. And lastly, the network subsystem design. Now, the physical topology is majorly concerned, the physical network design is majorly concerned with creating a physical topology design, selecting the hardware that is required for the project, selecting the links that are required for the project, and basic device configurations. So that is what occurs during the network design phase. Now, normally, this particular design phase is closely related to the project budget and the network performance. So it will make clearer how much is needed, because you're now selecting the devices, the links, and the performance is going also to be determined by the configurations and the type of hardware that you purchase and links. Now, the next stage after that is the logical network design. You need to do a logical design in terms of the LAN design and also WAN design. Maybe just to mention, when we talk of the physical network design, most of the time we are referring to layer 2. Physical, what am I saying? Not really. Anyway, when we're talking of logical network design, most of the time we're talking about the protocols actually. Most of the time we're talking about the protocols. So for example, LAN design, we're talking of, for example, things like how you're designing your IP addressing scheme, or also WAN design. Routing structure is how traffic is going to be routed within your network. Network egress design, how network is going to leave, how traffic is going to leave your network. And also we plan about availability, high availability design. So we're going to go through each one of them in a short while. Then network subsystem design includes things like network security, virtual private networks, wireless LAN, data center design, and also network management design. So in this topic, we are really going to go through each one of these particular design components. So some of the key points in network design is number one, the functionalities of the network and the performance. So here we are considering things like the throughput, the delay, the jitter, the bit error rate, etc. And the main objective here is to strike a balance between high performance and the cost of the project. So that is what we're supposed to do here. Number two, we have cost effectiveness is also a component of network design. So for example, the human cost, so for the engineering team, material, for devices, any financial resources, as well as construction period. So in terms of time. Then we also have these factors that has to be taken into considerations. For example, the reliability of the network, which is normally determined by the mean time between failures, MTBF, mean time between failures, mean time to failure, and mean time to recovery or repair, as some people call it. So we are going to look deeper into these terms in a subsequent slide. Scalability, same as extensibility. So when we are designing our topology, our network addresses, the protocols, so we are supposed to do that with extensibility or scalability in mind. So again, we're going to look at examples of how to cater for that. And security is also an important design factor. So physical security of the assets, any risks like fire, flooding, and their countermeasures should also be identified during this phase. Manageability, how you manage your network, most of the time, or one of the most common protocols that is used is SNMP, using a network management system like eSite, which we looked at. Most of them are GUI based. One of the protocols that IETF I think is still working on, I'm not sure whether it's a standard already, but is netconf, net configuration, which is most probably going to replace SNMP. To manage your network, you can also consider using a software-defined network, SDN. So those are some of the key points that you're supposed to consider, consider when designing your network. Now let's begin with the physical network design. As I said, we're going to look into each of these components. So physical network design. So this is the typical architecture of a small scale network. So physical network design really, you see, other than the topology, we're also going to look at how to select devices, how to select the links, and how to label the links and the devices. So this is the typical architecture of a small scale network. When you talk of a small scale network here, we are referring to a network that is supporting a small number of users, typically less than 100 users. Other characteristics of a small network, they are only within one location, for example, one building or one room, like a cyber cafe, for example. They do not implement a hierarchical network architecture. They implement actually a flat layer. So we don't have any hierarchy here, like the core layer, the aggregation layer, and the access layer. So everything is simply connected to this central switch, which is now connected to the internet via, for example, a firewall. So we don't have a hierarchical design. The requirements for this particular network are simple. So for example, if you're configuring, a good example of this, by the way, is for example, a cyber cafe. If you're setting up a network for a cyber cafe, they only want it in order to enable their devices to access the internet, and for example, be able to also access a shared printer or a shared server. So for example, this server might be monitoring their time so that it can be able to charge or something. So it's a very simple network, and this is how it actually looks like. You can also configure an access point, a wireless access point, so that anyone that is coming in with a laptop can be able to be connected to the network and to the internet. So this is called a FAT access point, because it can be able to issue IP addresses and do a number of other things. We're going to see the difference between a FAT and a FIT access point in a later chapter. So again, for security, you can just implement a firewall here, which is now connecting you to your ISP. This device here can be a switch or a router, by the way. So it can be a switch or a simple router, for example, that supports switching, routing, and generally can be able to offer such services. So that is a small scale network. Let's look at a more complex one, a little bit complex. This one now is what we call a medium scale network. When you talk of a medium scale network, these are the characteristics. Now, you need to know that this is one of the most commonly used. So number one, we have multiple functional areas. So for example, you see we have a server area, we have R&D department, marketing department, we have service department. And normally it is hierarchical. So here we have the core layer, we have the aggregation layer, and we have the access layer. Now, medium scale supports hundreds to thousands of users. So actually, most of the medium-sized universities use such a network architecture. Okay, let's look at another one. So here we have what we call a large-scale network. Characteristics: wide coverage, range, large number of users, complex network requirement. So you can see that we need to provide wireless internet access. We have a data center within the network. We have remote campuses. We have a branch in Kisumu and Nakuru. We also offer remote access to our lecturers, so that when they want to update marks from their home, they can do so through a VPN, either through an IP security VPN or an SSL VPN, which they can install in their laptop. You can also see that we implement redundancy. We actually connected to 2 ISPs. Now, actually, most campuses, most universities that have grown beyond reasonable doubt implement such a large-scale network architecture. So they have comprehensive and functional modules, and they have rich network hierarchies. So those are some of the characteristics. Those are some of the characteristics of a large-scale network. Most notably, redundancy. Redundancy is important. You can see even between the layers we have redundancy. Then the other thing is expansion or scalability. So because it's organized like this, you can be able to scale by adding switches at the lower layer of the hierarchy. So extensibility is also a key factor in designing a large-scale network architecture. Okay, so this is the traditional, what we are calling the traditional, but it's the most used actually. The traditional 3-layer architecture, where at the very top, we have the core layer, where we have layer 3 routers that are used to get traffic from our network to the internet, and from the internet to some part of our intranet. Then the second layer, we have aggregation layer. So all traffic aggregate here before they are routed to the core layer. Then we have this, they're called access switches, and they are at the access layer. So normally, again, here we have routers or a layer 3 switch. Here we have layer 3 switches, and here we have layer 2 switches. The reason as to why these are layer 3 switches, or this can be layer 3 switch or a router which is a layer 3 device, is because between the aggregation and the core layer, we do routing. We forward packets based on IP addresses. But here, we can forward based on MAC addresses. So that's why these are simply layer 2 devices. Okay, let's look at the next one. So you can, for example, see that from this hierarchical design, one of the biggest advantage of this hierarchical design is extensibility or scalability. So for example, if we want to open another lab, we simply connect a cable to that switch. We want to open another lab, because this switch will be, for example, 24 ports, and we've only used 3. So you see, it can really be extensible. In fact, other than tapping it directly from the aggregation layer, you also have a chance of doing it this way, but it's not recommended. So you can also extend from this switch. You add another switch here. So that's one of the main advantages of a hierarchical network. You can actually also do a switch there, then you pick it there to do another one here. Okay, then the other one that is becoming more common nowadays is called the 2-layer architecture, also known as the flat layer or flattened 2-layer network architecture. So in this particular architecture, we simply have the core layer and the access layer. So we don't have the aggregation layer. So the core layer routers are actually connected to layer 2 switches at the access layer. Now, this kind of hierarchy is actually very important and is majorly used in data centers to connect peer devices like storage devices, processing devices, and all other devices within a data center. It's also used in metropolitan area networks and also wide area networks. So simply put, it's also used with ISPs. Within the ISP network most of the time, this is the kind of architecture that you're going to get. So some of the advantages is that it provides a higher port density from a large number of access devices. You can see all these devices are, for example, 24 ports. So it provides a higher port density, and also it forwards data faster because it's only forwarding between 2 layers, and it can be able to connect devices, peering devices. Okay. So these are some of the common network topologies. You need to understand the advantages and disadvantages. The first one here is called a star topology, where you have a central device, and the other network equipment are being connected to that central device. If I go back here, you can see that actually what we're having here is actually a star topology. Star topology. Star topology. So that's what we call a star topology. One of the disadvantage with star topology is, for example, if this central device goes down, then all these people are not going to have network access. So that's called a central point of failure. Central point of failure. To avoid a central point of failure, you can implement redundancy in what we call a dual star topology. So this is a dual star topology. You can see that these ones are connected to at least two central devices. So that's why it's called a dual star. And actually, if I go here, let me go back so that you see that. You can see that between the core and the aggregation layer, we normally implement. So you can see we have that one. So that's a dual star. This one is also a dual star. So this device is connected to that one and that one. This one to that one and that one. This one to that one and that one. So even if this links goes down or this device goes down, these people are still going to have network access. So that's the main advantage of dual star over the star topology. Then in data centers again, we might have the square-shaped topology, which also provides redundancy, or ring topology, which might look like that. And the other common topology is the bus topology, where every device is connected to a single central link, which is referred to as the bus. So you should understand the advantages and disadvantages of these particular topologies. For example, this one, if the link goes down there, then some people are going to be isolated. Similarly to this, and maybe also this one. This one, if this one goes down, what happens? With the ring and also this one, other than the link, if this goes down, again, it fails. If this goes down, it fails. Here, if this guy has to talk to this guy, they can still talk even if this guy fails, because they're simply sharing the backbone, but not the particular device. So let's look at this case study. Can someone read for us this case study?
A university needs to build a campus network to cover areas such as teaching buildings, dormitories, and canteens, as well as branch schools and equipment rooms. How to determine the campus network scale? How to do that?
Just stop there first. So the scale, do you think the university network is small scale, medium scale, or large scale? Anyone? We've just mentioned this a while ago.
Medium.
Okay, I said it's medium. Most of the small universities use medium, but actually most campus networks are actually large scale because they have different network modules. For example, the wireless network module, they have a data center module, and they have they actually divide their network in terms of services. So you have the student network, you have the finance network, you have the research and development network, you have the procurement network. So actually, the university network is a large scale network. In this particular example, they're telling us it covers areas such as buildings, dormitories, and canteens. And I'm sure you know that, for example, buildings in a university, they are quite far apart. And they also have a branch campus, and they have equipment rooms. So actually, this is a large-scale network. So how to design the campus network architecture? Should we use the 3-layer or 2-layer architecture? Yes, anyone? Yeah, 2-layer or 3-layer? Okay, so the answer is 3-layer. 2-layer, we've said, is best for data centers and ISPs networks. Then which topology should we use? So if we're using the 3-layer, of course, we are going to use the star topology between the access and aggregation layer, and the dual star between the core layer and the aggregation layer, in order to ensure that we have redundancy and improve network reliability. So really, then that answers these 3 questions. Anyone with a question on this scenario or a comment? Okay, thank you. Okay, so let's look at device selection. How do we select a device? How do we select a device? Now, before we look at how to select a device, we might first of all need to understand some of the devices that make up a network. Now, the most common is what we are seeing here. So you might need to purchase a layer 2 switch, a layer 3 switch, and a router. So these are the most common. We also have other devices that you might need to purchase depending on the size of your network project. For example, we have firewalls. Most routers can still act as firewalls, but that is not their main function. So you might still need to buy a dedicated server that will act as your firewall. You might also need to buy an intrusion detection system or an intrusion prevention system. Definitely, for example, for a campus network, you need to purchase access points to offer wireless network access. And you also need to purchase, for example, access controllers. Access controllers are used to provide a unified management of the access points, so that you don't have to log in and provide a password at every Wi-Fi location that you go to. Now, once you're a student and you've logged in once to one Wi-Fi, then if you go to a different classroom that is on a different location, you're still going to be connected automatically. So that is the purpose of the access controller. So layer 2 switches, normally they look something like this. Layer 3 switches can forward also based on IP, and Huawei, they have a range of products and also routers. So we're going to look at some of these products just now. Now, we need to understand the architecture of switches, which actually determines how fast they are able to forward data. Now, we have 2 architectures that determine how switches forward data. One of them is called the bus architecture, and is what is displayed here. Now, the bus architecture means all the switch interfaces, what we also call ports, they are connected to a central connecting a backbone, which is called the bus. And therefore, only one of these interfaces can be able to use this particular central connecting bus at a given time. So they cannot simultaneously exchange data with this kind of architecture. So in order to access the bus and manage access to the bus, they use a bus arbitration algorithm. So there's an algorithm they use in accessing it. Now, that is the bus architecture. Now, some switches, current switches actually nowadays, they use what we call the switch fabric, which is called the matrix architecture. So here, interfaces are connected using dedicated lines to the switch fabric, and therefore they are able to access the CPU and the memory independently, and thereby they can be able to simultaneously exchange data on multiple ports. So while the bus architecture is simple and cost effective, it has poor scalability and is normally used in low-end switches. So when you're purchasing a switch, please make sure you consider, is it forwarding data based on the bus architecture or the switch fabric or matrix architecture? On the other hand, this one is quite expensive, used on high-end switches, but eliminates the bottlenecks of a shared bus, and therefore is able to forward data simultaneously on multiple ports, thereby improving the throughput. So this is about throughput actually. Okay, so let's look at some of the key points that you need to consider when purchasing a switch. So key points that you need to consider when selecting a switch. Number one, you need to look at the type. So is it a fixed switch or a modular switch? So fixed switch means you cannot be able to add components. For example, you cannot be able to add interfaces and cards, power supply interfaces. You cannot be able to add anything. Everything is fixed. Modular switches, on the other hand, provide you with that functionality. You can be able to add interfaces. You can be able to do power supplies and even the chassis, the entire switchboard, you can be able to stack another one. So that is what we call a modular switch. Then number two, the function. So does it forward only based on layer 2 addresses or layer 2 and layer 3? So again, on the access layer, we use layer 2 switches. On the aggregation layer, we use layer 3 switches. Then port density, the number of ports. Normally, they come with 8, I think 14, 28, going forward. We even have 48. So depending now on your requirement, and here you need to consider scalability of your network. So you need to purchase a switch depending on the layer that it's going to be installed and the number of people it's supposed to support. Then the portrait. So for example, if you want to purchase an access switch that is going to connect a computer lab that has 30 machines, you see, you cannot buy a switch that has 24 ports or interfaces. You need to go for the 48 ports. But for a layer 3, for an aggregation layer switch, maybe you don't need to go to 48 or even 24. Maybe you just need, for example, 8, because maybe you have 2 aggregation layer switches. So port density is an important factor, and then the rate. So the interfaces can transmit at 100 or 1 gig or 10 gig and so on and so forth. So generally, At the access layer, we use either 100 or 1 gig. Then when you go to aggregation layer, 1 gig or 10 gig. At the core layer, we can use more faster port rate because all the traffic from the entire network is being aggregated at the core layer. Then the switching capacity, what we've just talked about right now, is it using a switching matrix or is it using a data bus? And as I've said, this affects the throughput. Then packet forwarding rate, so the actual forwarding capability of the switch. Also, you look at things like the memory and the processing power of that particular device. So those are the factors you consider. Any comment or question? Any comment or question? Okay. Now, these are some of the Huawei fixed switches. This is called the S series. S series. Now, generally, the higher the number, the better the device. The higher the number, the better the device in terms of functionalities, and also the more expensive the device. So this one is just a layer 2 device, S2700. I'm sure in your labs, most of the time you've been using S5700. So this one, it is a fast Ethernet switch, meaning it can do up to a maximum of 100 megabits per second. And it can come with 8 interfaces, or 16, or 24, or 48. It can as well provide 4 gigabit Ethernet uplink ports. Now, gigabit Ethernet uplink ports, an uplink port is used to connect you to a higher layer. So for example, this switch will be used at the access layer. So these four gigabit uplink ports are used to connect to the upper layer, to the aggregation switch. So I hope that is clear. They're used to connect to the aggregation switch. So it will come, for example, with I've not counted this, but let's say these are 16 ports. But also, so these ports are used for downlink, for connecting to the end devices. But these ones here, you use them to connect to the aggregation layer switch. So I'm not going to go through all of this. You can have time and look at them. But as I've said, the higher the number, the more expensive. So for example, you can see this is a layer 3 switch. It can do up to 10 gigabits per second. So, and it also provides optical ports. So fiber ports. So those are some of the things that you also need to consider. Then these are the modular switches. Again, the higher the number, the more complex the switch. So what you need to understand is that most of the time, these modular switches are used at data centers or at ISPs networks and so on and so forth. So they're quite complex and they're able to do much more than the fixed switches. So you can see, for example, their interfaces can provide up to 40 gigs. So those are super fast. Their processing power, their processors, their power supplies and fans have a redundancy design, meaning you have more than one fan. If one goes out, the other one will still take care of the device. And all modules are hot swappable. So hot swappable means you can be able to change them or replace them without shutting down the device. You simply pull it out, the one that has malfunctioned, you pull it out and you install another one while the machine is still on. So you don't have to power off like we do with most other devices. So you see, you can also, that's why it's called modular. You can also add other chassis boards, and each chassis board can provide a maximum of 480 10 gigabit Ethernet ports. So they support advanced network principles such as MPLS VPNs, traffic analysis, quality of service, and multicast data and configuration. So they're normally used at the data center and ISP networks. Routers, when you want to buy a router, what do you look at? Not very different from a switch. So again, type, is it fixed, modular, or cluster based? The port type, does it provide Ethernet, serial ports, POS, packets over SONET, or PON, passive optical network ports? So depending on how you are connecting, especially to your ISP, you need to consider. So we're going to see ways in which you can connect to the one and which ports are needed. But in the meantime, just be aware that we have Ethernet ports, serial ports, POS, and PON. So we're going to see later how each one of them are used. Okay, then we have port density. So the number of ports that is supported by a single router. So like, for example, Ethernet ports are used to connect to your aggregation layer. Then these others can be used to connect to the outside. And some of them can also be used to connect to the aggregation layer. So the number of ports will determine how many devices you can have at the aggregation layer. So consider future expansions when you're considering the port density. Performance, so switching capacity and the forwarding performance of that particular router also depends with the switching matrix that the router is using. So other functions that you're supposed to consider is whether the router supports firewalls, intrusion prevention systems, VPN, online behavior management, voice, PBX for phones, and SIP. Now, these are extra functions, but they are not the main functions of a router. The main function of the router is packet forwarding and not packet filtering, like what a dedicated firewall or IPS is supposed to do. So generally, don't overwhelm your router with these other functionalities, otherwise it's going to affect its forwarding performance. So for these other things, please, if you can, and the institution is able to, let them purchase a dedicated device for that particular functionality. Then we have the AR routers, AR series routers. We call it AR series. Again, the higher the number, the more complex, the more functionalities they provide, and the more expensive it becomes. So allow me not to go deep into this. When you have time, you can read and understand some of those functionalities. Then we have this one, NE series routers. These ones again are used for are used at ISPs, networks, and also data centers that require a lot of bandwidth, redundancy, and such like things. So the following links provide product documentation of different types of devices. For example, routers, switches, security products, wireless products. So if you click on any of this link, it will take you to the Huawei website, and you can be able to see great details about these devices. Some time back, I visited the Huawei website and actually found they actually have 3D virtual images of these devices, and I really liked it. In that you can actually remove components, go inside the switch. I think I'll share that link with you, but it's a very nice simulation that they have there. So you can be able to go through a product like you have it with you, but you're actually doing it via their website. So it's actually a great environment that you can use to explore some of these devices. So after device selection, we need to look at media selection. So we can look at media selections, then network ID, and then we proceed for a short break, and then we come and look at logical design. So these are common media types. I'm not going to dwell here a lot. We've already talked about this severally. Twisted pair, we can have shielded, like this one here, or unshielded. Twisted pair, those are the two major categories. We know that we have several classifications depending on the distance it can cover and the bandwidth. For example, Cat5, Cat5e, Cat6, etc, etc. So you should be able to know when to use which particular type of cable, depending on the switches, for example, that you're interconnecting and the layer at which you are interconnecting them. Then we have the optical fiber. The optical fiber transmits using light. I know you already know that. We have single mode and multi-mode. One way in which you can differentiate a multi-mode and a single mode is the color. So they're color coded. When you see orange, you know that it's a multi-mode. It's a multi-mode fiber. When you see yellow, when the color is yellow, you know that it's single mode fiber. So single mode can be able to transmit up to a maximum of 500 meters. No, actually up to about 70 kilometers, but multi-mode only 500 meters. So that's the major difference. And of course, we covered this during HCIA. We also have wireless when you're using radio signals. In traditional networks, we might also have existing telephone cables that you might want to use for certain functionalities. And we also have the coaxial cable that you might use, for example, for video, especially for CCTVs. Most of them are still using coaxial cables, and they're actually part of our network. For wireless, you can have wireless LAN, or some campuses which are big are actually implementing LTE. LTE, which is what we are using with our phones, like the 4G. So again, those are the options on wireless. So let's look at the structural cabling in a building. Please remember this. The cabling subsystem in a building can be a horizontal or a vertical subsystem. So we actually have three: horizontal subsystem, vertical subsystem, and work area. No, not really. Let me end at this. We have horizontal and vertical. So you see here, we have a building that has 2 floors, actually 3 floors: ground floor, first floor, and second floor. So these particular cables that are interconnecting these switches at different floors is what you're calling a vertical subsystem. So it moves from equipment rooms in the floor to the central equipment room. So this one. Then we have this one that is moving from what we call the information panels or patch panels in the equipment room to the floor. So this is what we're calling horizontal subsystem. Now, if you don't know what a patch panel or information panel is, please Google about it. There's a YouTube video whose link I'll share in the group. so that you watch it. But if you just search on YouTube, what is a patch panel, you'll be able to get what that is. So generally, cables are connected to the patch panel. From the patch panel to the switch, then from the patch panel to this, to these sockets. Then now from the sockets, we have a cable that is running from that socket to your computer. So that's what we are calling our work area subsystems. From terminals to an information panel. So this is also, we are calling this an information panel. It's an RJ45 socket. So those are the three: horizontal, vertical, and work area. Now in data centers, we have two main techniques that are used to manage cabling. One of them is called top of rack. The other one is called end of rack. So top of rack is when access switches are installed at the top of each rack. So what that means is you have an access switch here. Then all these are machines. These are servers, for example, or storage devices. So each one of them is connected to the switch. So we have a line running. We have a line running from that server to the switch, from this server to the switch, from this server to the switch, like that. So that's what we call top of rack, because the switch has been installed at the top of the rack. Then we have end of row, where the switch has been installed at the end of the row. So all the servers are connected to the switch at the end of the row, at the end of the row. So those are the two cabling structures for a data center. So I'm giving you a reading assignment. Try and find out the advantages and disadvantages of each one of them. Some of the engineering tools and tests that you need to be aware of when you're using twisted pair. You need to know this information panel, which is called a patch panel, this socket, the rack, for example. So that is the engineering equipment that you need to know. And for testing twisted pair cables, we use this twisted pair test that is used to test and find out whether the cables have been crimped correctly and whether it's working, whether each of the cable is actually able to transmit electrical signals from end to end. So normally you'll plug one end here and maybe another end here. Then we have indicators here. Because it has eight, there are 4 pairs. So it has 8 lines. So we have indicator for each line. So it's gonna show you this one, it's gonna light one by one. Ta, 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 ta. So this is one of the tools that is used for testing. Then we have the optical fiber. For the optical fiber, again, we also have what we call a fiber management tray. And we have several types. We have several types of connectors. For twisted pair, the type of connector is simply RJ45. RJ45. For fiber, we have several. For example, this guy here is called an LC connector or lucent connector. How you know it? It is made up of a small square joint. So LC. Then this one is called CS, or subscriber connector. It has a large square joint, large square. Then you have a fiber channel. So you can see this one, it's rounded, fiber channel. It's round. Then this one is also round. It's called ST, or straight tip. So just to mention those again. So we have lucent, sorry, we have lucent connector, we have subscriber connector, we have fiber connector, and we have a straight tip. So normally they'll just be referred with the acronym. For example, LC, CS connector, FC connector, and straight tip ST. So a reading assignment again, I want you to read about these connectors and find out in what instances is each one of them used. Now, for fiber, we normally have this tester, or you can actually also use a laser torch. So if you use a laser torch and you light it up on one end, it should be able to produce that particular light at the other end. So for example, you can use that to check for continuity test, just to make sure that that particular fiber has not broken at any point. Then for a more advanced test, you can use this particular tester that can tell you actually the strength of the signal as it's transmitted along the fiber. The cost of this toolkit, testing toolkit, is about 3,000 to 2,000 to 3,000 Kenya shillings there. One of the basic network equipment tool that any network engineer should have, and also a crimping tool. So a network toolkit that has that tester and a crimping tool for RJ45 and other essential will cost you around 6,000 in town. So telephone and coaxial cables. So we still look at this because some networks still use them. So for telephone, anytime you're using telephone cables to transmit data, they have to use a modem because they're using different types of data. And we normally use a telephone cable loop test, which is used to find out if the current is flowing. So one end and the other end is connected. Then if they're able to light up, then you know that it's actually okay. Then you have coaxial cables. These are some of the testing equipment that are used to interconnect the connectors there. Okay, so let's end this topic with this subtopic on network ID. So network identifier, here we are talking about device identifier. We are also talking about line identifier. Okay, so this one is important. Now, generally, the network is most likely going to grow and things are going to get messy if we don't plan how to label or how to identify our devices. Now, generally, we have two ways in which we can do this. Normally, we do what we call a logical device name and also a physical device name. So a physical device name is simply a physical label that is actually stuck on the device to display information about the device. On the other hand, what you configure on the command prompt of that device using this command is what we call the logical name. So the device identifier is a unique identifier of a device on a network. So the physical label and the logical device name. So for this, you need a unified rule, naming rule, a unified naming rule. One of the most common example of a naming rule is that you begin with the device installation position. For example, this device is at the headquarter. So the installation position, then the role, for example, CS for core switch, then the model. What is the model of this device? So it is Huawei 7 blah, 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 like that. Then the logical number. So for example, the core switch, at the core layer, you have two switches, but this one, you're choosing it as number 1. So that is how you do a logical name. Now, for example, for a physical label, you can do device model. You write the device model, the device ID, so which is number 1, for example, and the responsible. Sorry, responsible person or contact information. Contact information. So this is what you do when you're doing a physical label. So always make sure this is done. Labeling is good because it helps, because it makes it easy to maintain and upgrade the network in future. It also makes it easy to troubleshoot the network. So always make sure that this is done. You're also supposed to label lines, as you can see in this picture. So again, with lines, we can use a physical label, like what you're seeing here. You see these are physical labels. And you can also do a logical description by using the description command. So you go to a particular interface, then use the description command. Description, then to, then you're saying headquarters, CS, core switch, that number 1 on this interface. So the unified naming rule might be the local device name, the peer device name, peer device ID, the link role, and the logical number. So this one is also very important. Okay, so let's finish up with this. Then we proceed for a short break. So can someone read for us this scenario? Anyone?
Yes.
Yes, go ahead.
Device and link identifier planning on a campus network.
Mhm.
A campus network has a large number of devices and lines and requires a unified naming rules for device and line diagnosis and management.
Yes,
Design the naming rules for devices and lines.
exactly.
Yeah.
Okay. So device naming rule. So let me just give an example for device naming. So for example, you can use ACC to mean it's an access switch. Then you go to the location. So the location can be something like, for example, it's in the administration hall. I'm A for admin. It's in the administration hall. Then it's in the first floor. So maybe F1 for that. Maybe it is in room 2 or west wing or something like that. Then the device model, then the device number, for example. So that's an example of how you can name your device. You begin with the layer that it's in, then the location, then the device model, then the number. For the line, you can do, for example, 2. So it's going to the access switch, or let's say aggregation. So you're using AGG for aggregation, which is in admissions, admin block on floor number 1 on room number 2. So for example, this one is 5700. The device model is 5700 and it is connected on G0/0/2. So again, this is just an example. So anyone with a question or comment? Question or comment? Okay. Asanteni sana.